Welcome again. Today we are going to talk about real-time operating systems in distributed system. It is not exactly the same like a real-time distributed system because even if we are working with distributed systems, each operating system will be local and will act locally. It's something different if we have a small computer with many different nodes, which they are close to each other, then we can have a global operating system for all these computers. But if we have a distributed systems, which nodes are very distributed, very far away, then it will be not possible to have something like this. Every node has to have its own resources management. This is the operating system, and they have to have some kind of synchronization via communication. Just a second, please. Okay. For this presentation, we are going to use our operating system Rhodos as an example. Because Rhodos is a very simple operating system, so we can explain it very easily. We can see the content very easily. Rhodos is a distributed operating system. For distributed systems, it's a real operating system which is already in use in many satellites and many drones and underwater vehicles. So it's a real system. And we know it very well, therefore we can use very good as an example to explain what we are going to handle today. First, we are dealing with distributed systems. If we are dealing with distributed systems far away, the nodes are distributed very far away, then we have asynchronous distributed systems consisting of different processors and processes. We have no common shared memory or global clock. I said before, if we have everything very close together with maybe 10 different computer nodes in the same box, then it will be maybe possible to have a shared memory and to have a common clock for all these processors. But if we have a real distributed system like this, or maybe distributed in different parts of aeroplane or satellite, then we cannot have shared memory. Every node will have its own memory, and all communication has to be via some kind of communication links, for example, CAN bus or Ethernet or time trigger Ethernet or something like this. Exactly the same with the clock. We cannot have a common clock for all devices because they are distributed, physically distributed. So every every computer will have its own clock, and the time from computer to computer might differ, and then we have to find some kind of synchronization between these computers. Then we have unpredictable processing delays. We cannot be sure how long each execution of each process will take, sometimes long, sometimes short, and we communicate via messages, some kind of links between different nodes, and the communication delays are unpredictable too. So there are a lot of unknowns which we have to handle. Then it's really difficult to have a global time and global state to realize. So the global state is distributed in many nodes around physical distributed systems, so to have a consistent view on everything will be very difficult. Even more difficult if the rate of events is very high. So events are very fast, then the change of different, the state of different computing nodes and different processes are changing very fast, faster than we can merge all this to have a global view. Or maybe the event execution may be very short. So the execution of process may be only a few nanoseconds or milliseconds, and the communication might take longer than that. Therefore, we have only an approximation of the global view of the system. As said before, we cannot know exactly the global state of the system. We have only an approximation. The only way which we could have a global view is to stop all activities and make a snapshot, take the state of all nodes and compare all them together. But if we cannot stop the system, things are changing in different parts of the system at different times, then it's really almost impossible to have a consistent global view of the total state of the system. Okay, We have to estimate a synchronous distributed system on a synchronous system. It is asynchronous. Every node has its own time. It's difficult to estimate a global time. So the times from different nodes have different rate. So we have to build maybe the average or something like this. And this will be not exact. Not every node will say the same time like any other. They have a difference. And this can make a difference in the execution. And it's very difficult to estimate the global state. So we cannot make global snapshots of the system. Now let's talk about the operating system. What for do we need the operating system? First, it's an abstraction from interfaces on hardware. For example, for portability. So we don't know to handle with the registers of the CPU, and we don't have to handle with different hardware devices. We have interfaces, abstract interfaces, so we can change CPU, we can change hardware, we can change devices, and we don't have to modify the software. Then we have to manage the local resources. For example, the CPU time, which task is going to be executed when, the main memory, how much memory will get every task, disk space in case we have a disk, then where we are storing data and where can we find the data we have stored before. We have to manage the input-output bandwidth, so we have a limited communications way, and then we have to distribute this communication bandwidth among different tasks. Exactly the same with the communication from the network. So who is going to communicate when and how much time of the communication network may be assigned to each task. So in worst case, we could have one task which communicates all the time and all other tasks will be not able to send or receive data. And this is something which the operating system has to take care to avoid these bad situations. Then we have the distribution of resources. Maybe some resources, we have to lock some resources which are going to be used by another computers. This is going to come later. And we have to protect resources from unauthorized access or abuse. Maybe with bad intentions or maybe without bad intentions. But if the programmers make a mistake, it can change the content of the memory of other tasks. And to find such problems is really, really difficult. Therefore, the operating system shall have something like an encapsulation to avoid one task to change the data of other tasks. Okay, which kinds of operating system we have? We have single user or multiple user. In embedded systems, most of the time we have a single user. Multiple user will be with different access, different logins and something like this. But in embedded systems, we have a single application which shall be handled by the whole system, and therefore we can say we have a single user. Please do not mix with single or multitasks. We can have many tasks, many applications running at the same time. Some operating systems which are very simple, they have only one task, and all others have to wait until this task is concluded and the next task can be activated. In multiple tasking operating system, we have many tasks which may be running at the same time. Please do not mix with multi or single user. It can be single user and multitask, or it can be multitask and single user. So it's something totally different. This is only the protection who might access the system. Okay, in case of multitasking, then we have two options. We have cooperative multitasking, which each task decides how long it will be running and when it can allow other tasks to work. Or we can have preemptive multitasking. In the case of preemptive multitasking, the operating system will take the decision when to stop one task to allow other tasks to work. Okay, then beside this, we have the option between batch, other interactive systems, or real-time systems. These are three types of operating system. The batch operating system, it collects all actions which shall be done, and then they will be executed, maybe the whole night. For example, complex number crunchings. And then we have an interactive systems when we have an interface with the user, and then the user says when to start each action. So it's not pre-programmed, but the user will say, I would like to do this now or this now. Then we have the real-time systems, something like interactive, but they are not controlled by the user. They are controlled by some events and time events inside of the system. And then, of course, we have embedded operating systems, which may be in very small processors, in very small computers. Okay, and now the design. Those are the options. And now, how could be an operating system design? It will be a monolithic system, so everything will be a single space. Everything, operating systems, applications, and interfaces will be everything linked together and will be a single executable file. If it is monolithic, it's a single address space. Everything will be linked together, and there is no protection to avoid one task to overwrite data from other tasks. The next case is layered operating system. So we have different layers from different excuse me. Sorry. So we have different layers in the operating system. Some layers which are going to handle direct the hardware interface, some layer for communication, some layer for resources management, and so on. And each of these layers will be a different address space. And they can be interchanged without having to reboot the system. In the monolithic operating system, if we change something, then we have to reboot everything, the whole operating system. Then we have the option from kernel and microkernel based operating system. In this case, the operating system is a very small set of functions, and all other more complex functions are something like applications running on the top of this microkernel. So every request from every application goes to the very simple operating system, and this very simple operating system will forward this request to another system application. And this system application will execute this request, goes back to the microkernel operating system, and then we go back to the user application. Then we have middleware-based operating system. In this case, the central part is the communication. The operating system will do nothing more than forwarding messages. And all interfaces, all administration will be implemented in applications, and the operating system, the middleware, the communication layer, will just forward a request from a service requester to a service provider, and in this way the actions will be executed. And then we have virtual machines or hypervisors. This is something like an operating system, but not for different applications, but an hypervisor is an operating system for different operating systems. So in a hypervisor system, we can have many different systems running on the same hardware. And the hypervisor will activate one operating system with all its tasks, then suspend and activate the next one with all its tasks, and so going round robin, around to the next, to the next, to the next. Okay. Now let's talk about memory assignment. It depends if we have multitasking or single tasking operating system. The most simple case is a single tasking operating system, which was mentioned before. Let's say we have these tasks which shall be executed, A, B, and C. It is single tasking, so only one task will be activated at the same time, and this task will get all resources, all memory, all CPU time, and can do everything which it wants with the control computer until it concludes. So we have here the operating system, and we have some, in this case, very limited memory. Okay, then we take first the task A. Here is the memory from A, and the rest from here to here will be distributed from the heap and the stack. What is the heap and what is the stack will be explained later with more details. But the stack is what we need for functions calls. Every time we call a function, the data of this function will be allocated here on the stack, and the stack pointer here will be shifted to this point. So the next time we make a new function call, then the new variables of this function will be allocated on the top of the stack pointer, and the stack pointer will be shifted again. So when we are calling functions, the stack is growing from bigger numbers to lower numbers. And every time a function concludes, then the memory allocated in the stacks will be released and the stack pointer will go back. And so this is the stack calling functions and going back from functions, returning. The heap is what we use for dynamic memory allocation. And for the heap, for malloc and a release for non-memory, we are going to use all rest memory from this point, what is not directly allocated to the process, until the stack pointer. And if both pointers, the heap pointer and the stack pointer overlap, then we have a memory problem. So this application is requesting more memory than the physical memory of the system. Okay, and this is the case for single tasking, so all this is allocated to the process A. When process A is concluded, then it will be totally removed from the system, and then we take the same with B. So here, B will be allocated, and the rest of the memory will be left for heap memory and stack memory. And B will use all resources until it continues. Then B will be removed, and C will take control. And this is single tasking. Now we have multitasking operating system. In this case, all these tasks will be allocated to the resources of our computer. Let's assume we can distribute the memory we have in 3 different blocks. So each of these process will get one of these blocks. And then we have this situation. This is the process A. And then we have here the heap and the memory until the rest where process B begins, and exactly the same with process C. In this case, all of them have the same amount of memory, but normally it doesn't have to be. So for each process can request how much memory it will require for heap and for stack. So we can have different allocations here. So all these tasks will be allocated in memory at the same time. So they have to share the resources, and the CPU time will be distributed among these tasks. First, it will run A, it will be suspended, not concluded, you suspend it for a while, then B will run a little bit, then it will be suspended, and C, and then we come back to A. Okay, and then we have another case for reallocation. Let's assume we have this memory distribution, A, D, and C. And here we have left memory, free memory, because here was a process which was already concluded. Let's go back. For example, if B concludes, then this will be removed, and then this memory here is free for the next process. But if the next process is bigger than the memory we have left, then we have a problem. But then we can have relocation. We can shift this process to this place, and then we will have enough memory together to allocate it. For this reallocation, or to be able to shift processes, we need something like a memory management unit. And this is what I'm going to explain now. What is a memory management unit? The most simple case, we have a CPU and a memory. The CPU is generating some addresses to access the memory, and then the memory will provide data in the data bus, or the CPU will provide the data, and the memory will write in the addresses what the address bus is saying, and this comes from the CPU. The next step is to interrupt this memory bus with a memory management unit. So the CPU is going to use what we call logical addresses, and the memory management unit will translate these addresses according to some translation tables inside of the memory management unit to physical addresses. So the address 0 here, it doesn't have to be the address 0 here, it could be the address 1,023,000, and the address 1,000,000 shall not be address 1,000,000 here, it could be the address 100. So where everything is going to be allocated depends on the allocation map, which is here in the memory management unit. And this can be different from process to process. So, and then we have this case. I'm going to come to this case later. So this is our virtual memory. So we have the address translation, and from each address in the virtual memory, we can have another address in the physical memory. Let's take this example. Normally, every task will have addresses beginning from 0 to some number. And if you compile different tasks, every one will begin from its address 0. For example, it could be something different, but let's say it will begin from address 0 to some other address according to the size. And if we want to execute all these at the same time, then we have a problem because all of them are requesting the same addresses. Address 0 for the beginning, but address 0 for task A is not the same like address 0 for task B. They are different things because they are different tasks. And therefore, we need this memory management unit. So the task A will get these addresses. Let's say every this is a page. Let's say a block of 1000 bytes. Let's talk about byte 0, byte 1, byte 2. That will be too much. Let's say the first 1000 bytes, the second 1000 bytes, the third 1000 bytes. Okay, let's talk about pages in memory. Okay, then let's say the first process will be activated here. And then the page 0 from the process will be the page 0 from memory. Page 1 from process will be page 1 from memory, and so on until page 6. And then we start the next process, task B. And it has again an address 0, page 0, but it cannot be the same because it's already allocated to task B. So the memory management unit will know the address 0 from task B shall be mapped to page 12. On the address 1 to 13, and so on and so on. And then exactly the same, we start another task, task C, and task C has again an address 0, and it shall be something different. And the memory management unit will then map the address 0 maybe to address 6, 7, 8, and so on. And then we have something like shared memory. If they are working together, they have a common task, then they shall communicate somehow. And if they are in the same computer, then the most simple thing is they share memory. Then we could say, okay, the address 6, the page 6 of this task shall be shared by other tasks. It doesn't need to be the same address for all other tasks. This could be the address 6. It's page 6. For this could be again the address 6, a coincidence. And then it will be again the page 6 in memory. But for task C, for example, it could be the page number 2. And then the address memory management will know it shall be the same like this, so it shall be mapped to the page 6 of the memory. And there is something more. Maybe some pages will not exist. So the memory management unit knows, okay, if it accesses the page 0, it shall get a page 4. It shall get a signal, page 4 doesn't exist in this memory. We can have different situations. Maybe it really doesn't exist, or we have something like a virtual memory. In this case, not all this data has to be at the same time in the main memory. Some data can be in the disk. So as long as this page 4 is not used, we can read from the memory, write to the disk, and use the memory for some other task, which we need now. And then we have here the signal which says, if you access page 4, let me know because it doesn't exist. Then in case he needs data from page 4, then the operating system will be activated, and then it will see to get the data from disk and place somewhere here. Maybe let's place here at this place, and then remember the page 5 from this task doesn't exist anymore in memory. But first copy this to the disk. And when this task needs to access this memory, then we get it back from the disk to the memory, and then we can continue working. And this is how virtual memory works. And if we are using virtual memory, then we need a memory management unit, like explained here. Okay, now let's talk about processes. This was memory allocation. Okay, typically, if we have a single task, then this is the situation which we saw at the beginning. Just a second, please. This task get everything, and all other are not existing until this is concluded. then the next task will get everything, all CPU resources, on all other doesn't exist, and task B A has concluded already. And when this concluded, then we give all resources to task C. That is single tasking. If we have multitasking, then all of them are allocated and they shall be executed almost at the same time. Of course, we have only one CPU in this case, so we have to assign the CPU to task A for a while, then to B, and then to C, and then back to A. Maybe according to priorities, but we are going to come to this a little bit later. Okay, now the processes. Let's say we have 4 processes, A, B, C, and D. And we have as much memory or resources that we can execute at most 3 of them at the same time. So we allocate A, B, and C, and D has to wait until one concluded. B is the shortest, so when B is concluded, then C will get the place where B was, and then we can continue. But at any time, we have 3 processes, and the CPU will execute a little bit time for each of them. So we got the impression A, B, and C are being executed at the same time, but in reality will be something like this. We execute a little bit from A, then A will be suspended, and we execute a little bit of B. This is the time going on. Then B will be suspended, and then with C, and then we go back to A, B, C, and so on until B concluded. And when B is concluded, then it will be not executed anymore, and then we will allocate the resources to D, and then we execute D. And then A will be concluded, and then we continue only with B and D. And then C will be concluded, and from here to the end, everything is left for D. And so is how we make a multiplexing of memory and multiplexing of CPU time. Okay, and now how it works. Let's have a state diagram. For each of these tasks, we shall know it is running, it is waiting, or what shall we do. Everything begins with we create a new task and then will be admitted. Then we say this task is ready to be executed. But only one task is being executed at one time. All others are only ready. Then there is a dispatcher which selects one of the tasks here. Here we have a list of all tasks which are ready. This is the state machine for one single task. Okay, and then we select one task which is ready, and it will get the CPU, and then it will be running. Here at this point there is only one running task. And after running, it might be concluded, then it will be released, then the task will end, and we remove all resources from this task, from memory and from CPU time and from all lists. But before it is released, maybe it has to be suspended. So it was working and working, but other tasks are waiting. So we get a timeout, and this will go back to ready. Then we take another task from the ready list, and we bring them to running, and another task will be running. And we can keep doing this. Another possibility is this task has to wait, for example, some event. It needs data from a device, and the data is not there. Or maybe it says, I need to wait until a time point, for example, 12 o'clock. Then it will go from running to the state block, waiting for something which comes from outside. And then another task will be taken from the ready list, and it will be executed. At some time point later, this task was waiting for an event. This event will arrive. Maybe he was waiting for a signal from a device, and the device delivers the data, delivers the signal. Then we take this from block to ready. It's ready to be executed because the data which was waiting is already there. Or maybe it was waiting until a time point. When the time point arrives, for example at 12, it is 12, then we say this task can continue working, and then it will get ready. And the next time we have the possibility, this will be dispatched again, then we take it from ready and will be executed again. This is the most simple state diagram of task. The reality is something more complex, especially if we have shared virtual memory. Do you remember? It's possible that some data which the tasks need are not in memory, they may be at the disk. And let's go back. Sorry. This was the citation. And if this task access this data which is not there, then it has to be blocked, suspended until the operating system gets this data from disk to memory, and then it can be reactivated again. This is a new state which is more complex to this simple state diagram. This is the state diagram of every task in an operating system like Linux. So you can see Linux or Windows or something like this. So you can see it's much more complex. It has a lot of states, but doesn't care. We don't care about this now. We can just see it can be really, really complex. And now let's take another example about preemption or not preemption. Do you remember? We said we have several tasks which are going to be executed at the same time. Then one will be executed, all are waiting, then it will be suspended for a short of time, and the next will get the CPU, and then this will be suspended, and the next, and the next, and the next. To do this, we have two ways. We can have preemption, where the operating system takes the decision when a task will be suspended to activate another task. Let's assume we have two processes or two tasks. First, this will be working. Only one can be working at the same time because we have only one CPU. And then we get an interrupt, a timer interrupt from the CPU. Then the operating system will perform a switch. This task will be suspended for a short time, and then this will be activated until the next interrupt, and then we suspend this and activate this, and we continue doing this, and the decision when one task will be suspended to activate another is taken by the operating system, and this is what we call preemption. Let's go. So this is this loop here. It will be running, it will be suspended, a timeout, it comes ready, and then we take the next one. And this loop here is what we see here. This is a preemptive operating system. We can have a non-preemptive operating system. In this case, the operating system will not do this by itself, but every application has to do it when it wants. So this application will be executed, and at time point he says, okay, I can give the CPU, someone else shall be continue working. And this is a typical example of a function called yield. So this task will be suspended, and then we will activate the next one. The next one will take the CPU and every resources until it says, okay, let someone else continue working. I make a yield. Then the next one. And this may take very, very long. And if it performs never a yield, it will keep the CPU time for always. Until he says, okay, let someone else working, and then we can continue this. So if we go back to this situation, now it's not done by the operating system. Every task shall say when it's running, let someone else work. And then this task will be suspended, it comes to ready, and the next one will be activated. So the same loop, but now under the control of the task. And I think we know when every task will be suspended. The bad thing is, if we forget to be cooperative, then one task might keep the CPU for every time, and all other will never get CPU time. So all other will stay waiting and waiting and waiting. So the task has to be what we call cooperative and always yield to allow other tasks to work. In the case of robots, we prefer this preemption, because else the programmers has to write these yields and every time point where someone else shall be working, even if no one else is ready to work. So the operating system might take the decision, now I will activate someone else at any time point. The problem with this, it is not deterministic. We don't know when a task will be suspended to activate another one. But at the end, it's better. Okay, and now let's compare a standard operating system with a real-time operating system. And a standard operating system is what we use in the laptops, for example, Linux or some kind of Windows or who knows what, or Mac OS or something like this. They are implemented in different ways because they are target different applications. Let's compare. First, a standard operating system is optimized for efficiency and flow rate. So execute as many applications as possible at any time. The real time is optimized for time constraints. Do not execute everything as soon as possible. Wait until the time point when everything shall be executed. So this operating system is waiting a lot of time when to execute everything. This here tries to use all resources as soon as possible. No time constraints, normally. Then, when we have different, many system calls, many functions to access, for example, access something data from disk, then first we collect all this to make an optimal access. For example, moving the arm and the disk in which direction, which we shall get first and then next, and then to make it as efficient as possible. In real-time operating system, they don't wait. As soon as a request arrives, it will be executed, even if the sequence is not optimal. But most important thing is to execute everything to its required time point. And here is, we don't have this required time points. We have only to optimize the resources of the system. Okay, another thing is we can lock few resources. For example, a device may be locked, so only one process may access this device, and when it is concluded, then the next. And here it's not so critical, so we can lock resources for a long time. So each process locks a device and do everything which has to do with this device, and then it sets free. Here, it will be very dangerous to lock resources for a long time, because maybe many other applications will access a little bit of this device, but they have to wait for a long time until the first application has concluded doing everything with this device. So we have to try to make these locks of devices or any kind of resources as short as possible. Just access, get free. Access, get free as soon as possible. Okay, and here we have the situation for the standard operating system, the scheduling, so when will be executed which task, maybe not deterministic. It's not a problem. It's not important first then, and then, it doesn't matter. But for real-time operating system, the scheduling shall be deterministic. We shall know when will be executed what. And in this case, we can have time points or something like priorities. So the scheduling has to be deterministic. Okay, and then we have the scheduling gives every task an opportunity in real-time operating system. So every task which is waiting shall get the CPU. If we don't say this is more important or less important, every task shall be executed at any time point. Here in real-time operating system, normally we have priorities. If a task has a high priority, it shall continue working as long as it needs the CPU. It shall not be interrupted, even if many other tasks are waiting. Only if some other task with higher priority needs the CPU, then it will get it. Some not. Or until it concludes. Then another task might continue working. Okay, another thing which we have in normal operating system is this paging and swapping. This is virtual memory. What I said before, if we need more memory than in the physical memory, we can move some pages to the disk, and when we need them, we move other page to the disk and we load what we need to execute now. Of course, it takes time because every task will be suspended until the data goes to the disk and comes back to the disk and it can continue working. Therefore, it is not deterministic how long this task will take to be executed. And this is something we cannot have in real-time operating system. So when one task needs something in memory, it shall be in memory. So we don't have this swapping between memory and disk. Well, it makes everything more simple, but we can have no task bigger than the real memory, what we have. Here, we can have tasks which are much more bigger than the memory which we have. Okay. And this normal operating system, they are highly efficient, but they are very complex. As you saw, they try to optimize many things, especially this patient is very complex. And here we have only very simple solutions. So they are low efficient, but they are simple. If they are simple, they are more reliable. And another important thing is a crash in a normal operating system, it's annoying, but it's not catastrophic. So maybe you can lose one data, you lose the work of maybe 2 hours, but it is not a catastrophic. Here, a crash in an operating system, it is controlling an aeroplane or an atomic plant, it can be really, really catastrophic. So here we have to invest a lot to be sure crashes will not occur. And something important to reach this is to stay simple. And this is even if we have low efficiency, our operating system will be more simple. And if it is more simple, we have higher reliability and the chance for a crash is lower. So these two things come together. I wanted to show there are some examples when people are trying to mix complex operating system with real-time applications. A very common example is the real-time Linux. So it's called real-time Linux, but it is not a real-time Linux. In this, we have an hardware, and then we have a real-time kernel, which is not Linux. It's a real-time operating system. On the top of this real-time operating system, we are running real-time tasks, and like any of these real-time tasks, we have the whole operating system of Linux, with all services, everything which is very nice from Linux. And here we have all these Linux applications running on the top of Linux. But the critical real-time applications, they are not running on Linux, they are running on the top of this real-time kernel. So they are two operating systems together, something like an hypervisor. On the top of this hypervisor, we have the Linux and some real-time tasks. And because these real-time tasks are much more simple, complex things can be implemented in Linux, and then we have communication FIFOs to send requests for complex applications running on Linux, for example, access of cameras, webcams, or something like this, which are much more complex to be implemented in this, and then we get this data by FIFOs. And this is a combination of normal operating system and real-time operating system. But as you can see, it's not a real combination. They are two things running together on the same computer. Okay, now we know we need a real-time operating system, and then which one shall we use? If we take a look, for example, in Wikipedia, we find a very big list of real-time operating systems. Well, normal operating system, maybe the list is not so big. Maybe you have some types of Linux, Windows, on Mac OS, and that's all. Only 3. If you look for real-time operating system and embedded systems, then the list will be really, really big. Maybe one reason is because they are much more easier to implement, and therefore it's not so difficult, and every company is doing its own real-time operating system. It's not the same like a normal normal laptop operating system. It's so complex, so difficult that you cannot do that by every company. Therefore, we have so many real-time operating systems. Then if you take a look, which one shall we use? But if you take the list you can see here, we have Rhodos, one of many. Okay, why shall we use Rhodos? I said before, in this case we are going to use Rhodos because we know it very well. It's our own operating system, it's a real operating system, and it's so simple. One of the most important directives implementing Rhodos was make everything as simple as possible. And therefore, it's simple to explain, and therefore is what we are going to use here. Okay, this is why Rhodos. I said before, it was done as simple as possible. It's simple to understand, simple to teach, and it brings dependability, reliability. Simple things work surprisingly well. It's so simple, therefore we hope it will have very few errors. At the moment we don't know from any error, it's working very well properly. And a nice thing is minimalistic, so everything as simple as possible, but it has everything which we need in a real operating system. So we don't miss anything. And it's a modern operating system. It's object-oriented, implemented in C++. Many other operating systems are implemented with all paradigms used in C. It's the technology from 30 years ago. This is the technology from 10 years ago, but it's better than the technology of 14 years ago. The next thing is it has an integrated middleware for the communication. It's more than operating system. And this middleware is what we need for distributed applications, for distributed operating system. Therefore, we can say we are going one step toward distributed operating system due to this middleware communication. Then it's a framework. With a framework, it's a very normal software technology when you can use the building blocks execution platform. I'm going to explain this later. And this is what I said. It executes building blocks execution platform, so you can implement your applications as building blocks and just add, remove, add, substitute, move from one computer to other computer. This will be explained later in more detail. Okay, it's easy to interface to hardware because it's simply implemented, and something very special. It runs on many different hardware, on many different CPUs, and it's able to run on other operating systems. So if you have, for example, a Linux system, you can implement Rhodos on the top of Linux. Of course, it will not be as well real-time as running direct on the hardware, but you can implement and test everything on the top of Linux without having to use the real target hardware. And this can be very good for many people developing at the same time. Okay, something very important. We don't want crashes. We need fault tolerance. And the support of dependability and fault tolerance is a basic part of Rhodos. So it's implemented already in Rhodos to implement some kind of redundancy management to allow the system to be fault tolerant. And another thing, it's already running in many satellites run on underwater vehicles, so it's in real use. It's not academic project. Well, it was an academic project, but it's already in use in real complex missions. And it allows to build complex software as composition, just adding components. And we don't know where is the limit. Okay, at the moment, for this lesson, I'm going to conclude here. And the next lesson, then we are going to use Rhodos for the development of distributed real-time operating systems.